One of the most important rings we study is the ring of integers. It was our first example of an algebraic structure. The first polynomial ring that we examined was z sub x. We also know that the integers sit naturally inside the field of rational numbers, Q. The ring of integers is the model for all integral domains. In this chapter, we will examine integral domains in general, answering questions about the ideal structure of integral domains, polynomial rings over integral domains, and whether or not an integral domain can be embedded in a field.
Fields of fractions. Every field is also an integral domain. However, there are many integral domains that are not fields. For example, the integers z are an integral domain, but not a field. A question that naturally arises is how we might associate an integral domain with a field. There is a natural way to construct the rationals, q, from the integers. The rationals can be represented as formal quotients of two integers. The rational numbers are certainly a field. In fact, it can be shown that the rationals are the smallest field that contains the integers. Given an integral domain D, our question now becomes how to construct a smallest field F containing D. We will do this in the same way as we constructed the rationals from the integers. An element p over q, q, is the quotient of two integers, p and q. However, different pairs of integers can represent the same rational number. For instance, 1/2 equals 2/4 equals 3/6. We know that a over b equals c over d if and only if AD equals BC. A more formal way of considering this problem is to examine fractions in terms of equivalence relations. We can think of two elements in Q as ordered pairs in Z times Z. A quotient P divided by Q can be written as P comma Q. For instance, 3 comma 7 would represent the fraction 3 divided by 7. However, there are problems if we consider all possible pairs in Z times Z. There is no fraction 5 divided by 0 corresponding to the pair 5 comma 0. Also, the pairs 3 comma 6 and 2 comma 4 both represent the fraction 1 divided by 2. The first problem is easily solved if we require the second coordinate to be non-zero. The second problem is solved by considering two pairs, A comma B and C comma D, to be equivalent if AD equals BC. If we use the approach of ordered pairs instead of fractions, then we can study integral domains in general. Let D be any integral domain, and let S equal the set A comma B, such that A comma B are elements of D, and B is not zero. Define a relation on S by A comma B similar to C comma D if AD equals BC.